So we come now to section 3, which is the Bohr model of the atom. As a reminder, where have we come so far? We came from the atom being a marble, to an atom being plum pudding, to an atom being somewhat like a little solar system, to now, well, we didn't know, right? We've made so many discoveries, particularly the idea that energy is quantized, that we really needed a new model of the atom. And so Niels Bohr attempted to do that for us. So the Bohr model of the atom, which there's a hyperlink to a video, helps us to address some of these discoveries as well as some of the potential pitfalls that needed to be overcome. According to classical mechanics, an electron orbiting a positive nucleus would ultimately want to be attracted to it, right? Wouldn't a positive nucleus want to attract a negative electron such that the electron would eventually spiral into the nucleus and obliterate the atom? Well, we know that doesn't happen. So what's the explanation? Why does that not happen? Niels Bohr proposed the idea that electrons orbit the nucleus in fixed orbits. He based his model of the atom on hydrogen. But this idea of fixed orbits, this idea that electrons could not just willy-nilly orbit anywhere, but that they had to orbit in these fixed orbits, was congruent with the discovery that Max Planck made, and that was that energy was quantized. So an electron couldn't just be anywhere. An electron would only be in certain spots that corresponded to certain amounts of energy. This made sense. Now, the distance between all of these orbits were not equal. In fact, if you think about the orbits like rungs on a ladder or steps of a staircase, the distances between each level are not equal. In fact, the distance between the first energy level, or first orbit, and the second orbit was the largest. The second to the third was a little bit smaller. The third to the fourth, a little bit smaller still. And this would actually go on and on to a finite, infinite number of orbits that an electron could orbit on. That could also be illustrated here. So notice that these lines represent allowed orbits that an electron could be on if you figured the nucleus was down here. It's kind of like the rungs of a ladder. But as you can see, the rungs are not equally spaced. The largest energy difference would be between the first energy level and the second energy level. And it would get smaller and smaller as you got further and further away from the nucleus. So what are some basic ideas of the Bohr model of the atom? Well, first thing, each orbit is a different energy level. The further out from the nucleus electrons were, the higher in energy they were. The difference between energy levels is not the same, and we talked about the difference between the first and second is the largest transition. Thirdly, electrons in different orbits have different energies. Electrons cannot exist between the energy levels, so you could not have an electron existing between the first and second orbit. This would violate not only Bohr's model of the atom, but it would violate Max Planck's discovery that energy is not continuous. And finally, n equals 1 is the lowest energy level. This is going to be the energy level that electrons feel the most stable and secure, therefore meaning these electrons would have the lowest energy. Now, electrons do move, and they can move from one energy level to another. If an electron were to jump orbits, in other words, move away from the nucleus, it would need to absorb energy in just the right quantity. Think about this. You're an electron and you're feeling very stable close to your nucleus. For you, let's say your nucleus is your couch or your bed and you're feeling very comfy. You feel very stable, right? You wouldn't want to necessarily move away from your nucleus. That would be unnatural. You wouldn't, it's not natural for you to want to just all of a sudden be doing all the things and be stressed and trying to hit deadlines and do your homework. I don't know, maybe you do. I can't explain those exceptions. The idea is our natural tendency is to be stable and secure, and so is the electron. So if we were to expect an electron to jump and move away from the nucleus, we're going to have to supply some energy. The electron's going to have to absorb energy. Just like maybe we have to take a shot of espresso or splash some water in our face, the electron needs some energy to do that. And it needs it in just the right quantity. But also, electrons will drop orbits, meaning they will move closer to the nucleus, and to do that, they will release that energy that they absorbed. And the energy is always released in the form of electromagnetic radiation, which, what does that mean? Light. And it can release energy in all types of light forms. It can release UV, it can release infrared, but when it releases light in the form of visible light, this is things that we can see. And a practical application of all of this is fireworks. Fireworks are an example of this. We light the fuse and supply some energy to get the electrons all excited and jump away from the nucleus. But as soon as they have the opportunity, they will return back down to their stable state, and as a result of that dropping back down, the electrons release photons of light that are equal to certain wavelengths. Maybe some are purple, maybe some are red, and so on and so forth. And that's actually how we see fireworks. This release in energy is always in the form of the energy equation we saw earlier. That energy equation will help us determine what the change in energy is. Sometimes that energy is in the form of visible light, but sometimes it's not. Like I mentioned, it could be UV, it could be infrared, and so on and so forth. When electrons drop energy levels, we mentioned that they emit electromagnetic radiation, and often this is in the visible light. When this happens, it creates an emission spectra. In other words, it's going to produce a band of light that looks somewhat like this. All of these bands of light correspond to different colors, which means different wavelengths, which means different energies. And that can be illustrated right here. All of these light bands that you see here correspond to just different drops that an electron can do. For example, if an electron is simply dropping from this energy level 3 to this energy level 2, it will produce a red line. But if an electron is dropping from energy level 4 to energy level 2, it'll produce this bluish line, and so on and so forth. This actually creates almost like an atomic fingerprint, because every element will produce its own emission spectra. The reason for that is because every element has a different atomic structure. This is an example of 3 more elements. You can see that helium, zinc, and sulfur all have different emission spectra. That's because their structure is different. This explains why scientists are able to look out into the stars and planets and figure out what different planets and stars are made of. For example, you might hear someone say, Saturn is 87% hydrogen, for example. I don't know if that's true. But you will think, how do they know that? Do they go to Saturn? Do they get in a spaceship and analyze it? No, they're actually analyzing the light that is given off from Saturn. And by simply analyzing the light given off, we can figure out which bands are being created and thus which elements are present. Alright, so let's look at an example with all of this information. This is a great example because this example is going to test if you know your relationships. So it says, which energy transition would result in a photon of light being emitted with the highest wavelength? So, an electron going from energy level 1 to 2, 2 to 3, 3 to 1, or 3 to 2. So let's remind ourselves, and I'll actually draw it off to the side here as a ladder. Let's say this is n equals 1, this is n equals 2, and then notice n equals 3 would be a little bit closer, right? So we want to know which energy transition would result in a photon of light being emitted with the highest wavelength. Well, the first thing I notice is result in a photon of light being emitted. When is light emitted? When electrons get further from the nucleus or when they drop closer to the nucleus? Light is always released when electrons drop. So these first options where the electron is jumping from 1 to 2 or 2 to 3 cannot be the options because photons won't be emitted in those transitions. Only when electrons are dropping will they be emitted. So now we have the option of when an electron drops from energy level 3 to energy level 1, or from energy level 3 to energy level 2. Which one of those transitions will result with photon of light being emitted with the highest wavelength? So if we're looking for the highest wavelength, we're really looking for the lower frequency, which means the lower energy. So out of those two, this transition would be the one with the lowest energy. And so therefore, letter D is our option, our answer, 3 to 2. All right, that wraps up this section. We'll see you in section 4.